Okay. I think we're good to go. I think, yeah, we're good. We started talking about friction. We gave it like a little 10-minute thing, and I gave you you had a 10-minute spiel. I gave you the formula for friction. So I said that the force of friction on any particular object was equal to the coefficient of friction times the, no, no, no. Yes, the normal force. Yeah, it's because friction is fun, so it's the force of friction is equal to the coefficient of friction mu times the normal force n. Okay, that's why I put an arrow over here so that you guys don't think that it's newtons, because n without an arrow is the unit of newtons. N with an arrow is a vector, a force vector that says that this is the normal force on an object. And the normal force can actually occur in several different places. So, like, for example, if you are trying to hold something on the wall and you put a force on it, it'll stick to the wall. So, if I push on an object on the wall and I have an applied force, that's what they do with what? Yeah. Um, okay, so like there's two different cases. In that case, um, I'm talking about if you push on the wall and you keep it stuck there, okay? Because what you're doing is there is a normal force of the wall pushing back on the object, and these two forces counterbalance each other. The greater the applied force that you put on it, the greater the normal force becomes. And since the force of friction is equal to the coefficient of friction multiplied by the normal force, the greater you get the normal force, the greater friction becomes. Okay, so you can get friction to occur in greater magnitude by increasing the applied force. Now, there were those tricks that people were doing where they were taking the pencil and they were like sticking it on the wall and stuff like that. In that case, it's not really an applied force that's keeping it on there, but there is some kind of attraction between the pencil and the wall. The easiest one to explain is balloons. If you take balloons and you charge it on like your hair or something and you stick it on the wall, the force that keeps them together is the electrostatic attraction. So it's an electromagnetic force that holds it to the wall and keeps it stuck there. When you're talking about like a pencil, I I haven't really heard much about like the description of why that works. I don't think it's electrostatic. I think you're literally just heating up the. I think you're just heating up the pencil so much that you're putting divots in the wall, and it's just like staying stuck there. Um, yeah, because you have to push pretty hard. Like you can't. Whenever you do that trick, you can't just be like, and just like barely put your force on the pencil. You have to like really push it against the wall. So I think what you're doing is you're just making like these tiny divots and just like getting it stuck in place because you're literally grinding it in there. So I don't know. Just it could go either way. I don't know. So there are two main types of friction. Hmm. Yeah. There are two different types of friction. There's a static friction and there's a kinetic friction. Okay. Now, theoretically, there is a rolling friction too. But in AP Physics, I only really see static friction and kinetic friction talked about. So I'm not really going to say a lot about rolling friction, um, other than that it is easy to get something to roll. So rolling friction just really applies to things like wheels and tires and stuff like that. Anything that has a something rolling around it like in a circle. Okay. Yeah, a trackball mouse would totally be the same thing. You're not wrong. So static, what does the word static mean? So not moving. Yeah, still not moving. There's no motion. Okay, so we're still. Kinetic means it's got motion to it. Okay, and something really interesting happens. As it turns out, there are two different types of friction that are different from each other because of the motion that's occurring. Static friction is always a greater coefficient than kinetic friction. So whenever it comes to static versus kinetic, static is always greater than kinetic friction. It's always harder to get something started moving than it is to keep it moving if there is friction involved. So like correct. Yeah, so like whenever we were talking about the lab yesterday, in the lab yesterday we had a box and we pulled it, and at the very beginning the thing said 6 newtons, but then after you were moving it as time went on, it went down to what, 4? 4.5? Yeah, went down to 4.5 newtons. Okay. So in this case, the 6 newtons is going to be the coefficient of friction of the static part, and the 4.5 newtons would be the coefficient of friction for the kinetic part. It's crazy, but it worked. Like if you've ever taken something heavy and you've dragged it across a room, like a refrigerator or a washing machine or something like that, it's really hard to get it started at the beginning, and then after that, it's easier to push. Okay. And yeah, dollies don't count because that changes the static friction and it changes it to rolling friction. And rolling friction is the lowest type of coefficient of friction, so we don't really have to worry about it too terribly much. I've never seen a rolling friction question on the AP Physics test, so I'm going to just ignore that part. So static and kinetic friction. Um, so what this means for us is that we actually have to be careful on whether or not the object is moving or whether or not the object is not moving. Because if the object isn't moving, there is static friction involved, and if the object is moving, there's kinetic friction involved. And the two are actually different from each other. It's harder to get something started than it is for it to continue in its motion along that path. And the best way that I can try to explain it is whenever you actually stop it, those little microscopic divots inside the object's surface will actually like sink into place. So whenever you actually start moving it, you have to push them out of that surface. And whenever it's rolling, they just kind of like just bump over each other. But whenever it stops, they sink into place. Okay, so the static friction is always a greater value than the kinetic friction. Okay, they both have the same symbol, which is mu, but for static friction, we normally write this little subscript, mu sub s, and for the kinetic friction, we normally write this little subscript, mu sub k. So if you ever see mu sub s or mu sub k, that's what those refer to, static friction and kinetic friction. We have mus and muc. Yeah, mus and muc. Mucus, definitely. We should have put kinetic first, so it could be mucus. Mucus. Do what? Yeah, go for it. Okay. Um. So yeah. Um. Let's try. I mean, like, we can try a couple of these things. Um. The bad thing about this is that there's not really like friction problems in and of themselves. The friction problems uh, weave their way into the problems that we've already done. So like incline problems can have friction associated to them. Pushing something across a floor can have friction to it. An Atwood machine can have friction to it. All of these things can have friction added to it, and it ends up slowing it down. Okay, and we're going to actually have to take it into effect whenever we think about the objects themselves. Okay, if we don't have the coefficient of friction, then we're going to have to find the coefficient of friction. They would have to give us everything else except for the coefficient of friction. So do y'all want to try a problem with these, or you want me to try to explain friction a little bit more? What's up? Got any questions? Go ahead. Oh, okay. I thought I heard somebody say something. Hootie Wuddy, huh? Oh, that makes sense. That makes sense. That's what I just heard. Yeah, basically that's what I heard. Okay. So let's take an example. We'll do an example of a car, and we'll say that a car is actually like moving forward. And I'm going to say that the car is um, having an applied force from the engine of about, I don't know, 4,500 newtons. But I also know that this car is moving at a constant speed. So it's not really accelerating. It's not really decelerating. Why don't we just say that it's moving at 35 meters per second, just to throw a number in there. So it's moving at a constant speed of 35 meters per second, and the car itself has a mass of, I don't know, what's a decent mass for a car? Think about it. What's a decent mass for a car? A ton? Okay, what is a ton in mass? That is right. You can't say pounds. Yeah, you can't say pounds. Ish. 800 kilograms ish. Okay. Why don't we go with that? Why don't we say that the car has a mass of 800 kilograms ish, and we know that this thing is going at a constant speed. So the question is, what is the coefficient of friction? And I'm going to use, is it mu sub s or mu sub k? Well, which one are you going to get? Right. Yeah, it's moving, so you got to use kinetic. Very good. Yeah. There is no static friction right now because it's not standing still. It's moving. So there is a mu sub k value. There is not a mu sub s value. There's not a coefficient of static friction. So we're going to be asking ourselves, what is the mu sub k? How would we go about doing this? Pretty much. How are we going to start this? Do the what? Okay, so we know that's fair. We can start with something on the formula sheet that the force of friction is equal to the coefficient of friction times the normal force. Uh, and we could start with that. We're going to need a couple of other things. So I'm going to say, I'm going to ask myself a couple of questions. Is it moving? Okay, and the answer is yes. Next question. Is it accelerating? Why? Okay, so it says constant speed, right? So that means, is it accelerating? The answer is no. So what does that mean? If it's not accelerating, that means that either, according to Newton's second law, that is the third law. The third law will tell you that for every action, there's an equal and opposite reaction. This is not inertia. Yeah, inertia is the first one. So we've got the second law basically tells us that the sum of the forces is equal to the mass times the acceleration. So our acceleration is 0. So that means that our okay, so then that means that the sum of our forces is going to be equal to 0 because the acceleration is 0. So Newton's second law is what we need to use to kind of to give us an idea of what's going on here. Since this thing's moving at a constant speed, the sum of the forces in the x direction and in the y direction are going to be equal to 0 because this thing isn't accelerating in either direction. So that means that the forces are, I'm looking for a B word. It means the forces are balanced to each other. So if the forces are balanced, what's another word for balanced? Good. So how do I actually mathematically write that these forces are equal to each other? Okay, so I'm going to use the equal sign. What two forces are equal to each other? I did not write all the forces up here. Would y'all like to do that? Okay, so there's one force going up this way. What is another force acting on this object? I'm going to put a free body diagram down here. We've got FA. It is on the ground, right? So there's an FA. There is a Forces. Y'all want to use FG? Is that okay? What other forces do we have acting on it? Okay, there is a normal force because it is on the ground, right? So there's a normal force going up, and there is a frictional force going the opposite direction. Very good. Okay, so which two forces are balanced with each other? Okay, so we do have those. We have N is equal to Fg. That's true. And this is in the y direction. What about in the x direction? Are the forces balanced in the x direction? It's moving. Why? Okay, so like I got a yes and I got a no. They what? Why should they be? It is moving. It's moving at a constant speed. If it is not accelerating, so if it's not accelerating, that means that we are going at a constant speed, so our acceleration has to be zero, which means that these two forces have to balance each other out. Okay, so I know that my applied force, F of A, is equal to my frictional force, F of F. This only is happening here because of a constant speed. Okay, if it was accelerating, we could not do this. We would have to write that it's equal to the mass of the system times the acceleration, and we would be able to solve it that way. Okay, but since it is moving at a constant speed, then the applied force is equal to the friction force. What's the applied force equal to? Well, this shouldn't make you too terribly sad. Okay, so the applied force down here is equal to 4,500 newtons from up the top. So I know that 4,500 newtons is equal to, what's the force of friction equal to? The coefficient of friction times the normal force. Okay, and I'm going to have to put an arrow there. Because remember, this is a unit on the left side, and then on the right side, that is a vector. That's an actual force. Okay, well, we still have a problem. There's still two things that I don't know. So if there's two things that I don't know, I can't solve. You are close. We do know that the normal force is going to be equal to the force of gravity, but the force of gravity is not 9.8. It's going to be 9.8 times 800. Yeah, because f of g, and And honestly, I don't normally write this f of g as f of g. Every time I see an arrow pointing down for gravity, I normally just go ahead and I write out mg so that I know that those two things are multiplied together to each other. So mg is going down. So I'm going to say that, okay, 4,500 newtons is equal to mu mg. And I know that those two things are multiplied together. I have the mass and I have the, let's see, I'm going to try to squeeze this in. 800 times 9.8 meters per second squared. Those two numbers come out to something. 7,800? Okay, 7,840. Okay, yeah, I'm just going to not worry about the decimal. So we're going to divide both sides by 7,840, and that's going to give us our coefficient of friction in this particular case. So our mu sub k is going to be equal to 0.574. Good. Very nice. That would be how you would find an example of finding a coefficient of kinetic friction. Every time you're dealing with kinetic friction, you have to keep in mind that the free body diagram is going to dictate how you solve this problem. But no matter what, using Newton's second law is probably going to be very, very, very important for solving these force problems. Okay, so having an idea of what Newton's second law means and what it says will make a big difference. And you're either going to get the sum of the forces is equal to ma, or you're going to get the sum of the forces is equal to 0. If it's not moving, or if it's at a constant speed, the sum of the forces equals 0. If it is accelerating, the sum of the forces is equal to ma. Okay? Let's try one where we actually are accelerating. I think that's probably a good idea. Because we have an example of one where it's not accelerating. Now we need to make one where it is accelerating. So I heard you liked inclines. I think we should probably do one of those again. But let's revisit it to where evil friction comes into play and we actually have to calculate it. So let's see here. Well, make an incline like that. This side over here is a right angle. This side over here is at, how about 20 degrees? You want me to make it bigger? Okay, it's almost sounded like a complaint. Like, that's not big enough. We need to make it like a 50-degree incline. Oh, what? Yeah, I was about to say, what mentally competent person would carry a box up a 50-degree ramp, though? You know? Then people start saying, like, well, I carried it up. No, it's just, don't hurt yourself. Huh? We are going to let it go down the ramp because it's going to accelerate down the ramp. How big do we want this box to be? What's a reasonable weight for a box? 80 kilograms is not it's not a weight, and B, it's not reasonable. What is a reasonable weight for a box? 10 pounds? Okay. Now let's change that pounds to newtons. 5 kilograms? Okay. How many kilograms is mass? Yeah. You have to pay attention to the words that I say. I said weight, right? So what's a good weight in newtons? What's a reasonable weight? 10 pounds in newtons would be what? 50 newtons? Around about 50 newtons. Okay, we can go with that. 50 newtons is easily, you can pick up 50 newtons, no problem. Okay, that'd be about 5 kilograms. That's doable, very doable. Okay, so let's say that we've got okay, 5 kilogram mass, right? 5 kilogram mass. I'm okay with that. That would also be 50 newtons from gravity, right? Okay, it has a weight of 50 newtons. It has a weight of 50 newtons. It has a mass of 5 kilograms. We are talking about the same thing, right? Okay, that's why I'm just trying to, just getting you guys accustomed to this kind of stuff. Now we're probably gonna need a little bit more information about this in order to try to find the coefficient of friction. So, what other information are we gonna need? Because I'm gonna say my ultimate goal is to ask myself, what is the coefficient of kinetic friction? But if I just have the mass and I just have the angle, that is not going to be enough information to find mu sub k. Okay, we definitely need all the forces. So we have gravity, so we have the force that's pulling it down-ish. We'll have to break that up into components. We have the normal force. Do we have anything for the applied force? We do. It's weight. Yeah, the weight is going to be the applied force. Do we have anything for the frictional force? We are going to need something for that. We are definitely going to need something for that. So if we were finding the coefficient of friction, we're going to need one more piece of information. Okay, so let's say that we're going to need the force of friction, and I'm going to go ahead and just give it to us. Okay, I'll be nice to us. We'll say that the force of friction going backwards is going to be equal to um, 20, let's go 18 newtons. I'm going to make up these numbers and I'm going to pretend that it actually works out. I hope it does. So the force of friction is going to be equal to 18 newtons. If we were to draw a free body diagram, first of all, what is the line of action? Diagonal down. Okay, so like this is the line of action, correct? Okay, so when I draw my free body diagram is going to look like this. Okay, so my up and my down is going to be the black line, and my left and my right is going to be the horizontal line. Okay, so whenever I go, and here's my dot, okay, what force is pointing straight up? Okay, I don't know. The normal force is straight up, okay, in this case. If the line of action is going like this, okay, so if the line of action is right here, along this dotted line, okay, the one going down this way, this force down here is going to be not mg, right? This is going to be mg cosine theta. Okay, we have to use the cosine for that one because that's the adjacent side. Okay, and if y'all forgot, here's mg that points straight down like this. It makes a right triangle. So cosine is for the adjacent side, and sine is for the opposite side. That's where that cosine came from. Okay, now we have an applied force going this way, and that applied force is gravity. That's the force that's going straight down the line of action this way. Okay, what's that? This force is, it is related to sine theta, yes. It's going to be sine theta, but I need a couple of other things. It's what times sine theta? What is the hypotenuse of the triangle? It is not just acceleration. It is the force of gravity. Okay. So what is my force of gravity? No. Force of gravity. 50 newtons. Okay. So I can go ahead and I can change this mg cosine theta. I can change it to 50 cosine theta, and I can go ahead and change the other one. Are I think y'all are kind of fighting me on these letters here, so I'll just change this one down here to 50 cosine theta, and I'll change this one up here to 50 sine theta. Is that okay? Would you like me to change the theta to 20? If you want, you don't care. Whatever. This already hurts anyway. It is the angle. So it's going to be 50 sine of 20 degrees and 50 cosine of 20 degrees. That 20 degrees comes from similar triangles. We're breaking down the vector, okay, according to the line of action. Okay. And the other direction, oh, I hope I got this right. This is going to be 18 newtons. And I may have to change this around because if the force of friction is greater than the applied force, it ain't going down the ramp, Chief. So y'all do me a favor real quick. What is 50 times the sine of 20? And I hope it's greater than 18. If not, I'm going to have to rechange my force of friction. Ah, 17.1. Okay. Um, quick fix. The force of friction is not 18 newtons. The force of friction is 10 newtons. Yeah, let's use 10. We'll do that. As long as it's less than 17 point whatever, we'll be okay. But I can't like your force of friction shouldn't be greater than your applied force going down. I just when it like in the back of my head, I was like, oh, I need a force that's like less than 50. Let's go way less than 50. Let's go 18. Surely it can't be. It's totally less than 18. Um, I did. You're right. I should have gone for a steeper angle, but whatever. It'll work. It'll work. It'll work. Okay. So we have our four forces, right? We have 10 newtons. We have 50 cosine of 20. That's the same thing as the normal force. So whatever this number is, that's the normal force. And we have 50 sine of 20 for the line, like the force of gravity going down the line of action. So going down this direction. So we got 50 sine 20. We've got 10 going backwards for the force of friction. I think we have everything that we need. So the first thing I'm going to ask you guys is because I'm going to ask myself a couple of questions. So question number one is it moving? Is it moving? Okay, so it has an initial speed of 0, right? But as it goes, does it go down the ramp? Yes. Okay. So that's the first question. Is it moving? Second question, is it accelerating? Okay. So if it's accelerating, then we're going to do what? F equals ma. So we're going to do the sum of the forces is equal to mass of the system times the acceleration. Okay? We've already got everything graphed out, so we don't have to go like that's the reason why we graph stuff out in the first place, so that we don't have to like get down to this equation and then be like, "Oh crap, what do I do?" So, what are our forces? What is the sum of our forces as numbers? 50 sine 20 is the first force. Okay. So 50 sine 20. Okay. What next? 10 newtons? Negative 10. Why negative? Okay, left is negative, right? So we're going to be going negative 10 newtons. Okay. And that's going to equal what? Okay, the mass of the system is 5 kilograms. So we got 5 kilograms times. Yeah, that's what we're looking for, right? That's the story of the day. Because if we can find that acceleration, then we know how far that's actually going down the ramp. Okay. All right. Now what? do the thing. Yeah. What is 50 sine 20? I mean, 17.1 newtons, right? So we got seven. Y'all already found that one earlier, didn't you? 17.1 newtons minus 10 newtons is equal to 5 kilograms times the acceleration. Yeah, okay, so yes, we are going to subtract them. We're going to divide both sides by 5. So that is 7.1 divided by 5 equals the acceleration. So 1.42 meters per second squared. Okay, meters per second squared. All right, was that what I asked for? Really? What's mu sub k? So, okay. So we know that the force of friction is equal to mu times the normal force. Okay. Yeah, so like the normal force is this force going up this direction, right? And we already know that it's 90 degrees to our line of action. So that is, what is it again? Okay, that's 50 cosine 20 is 46.98, right? Okay, 50 cosine 20 is 46.98. So that's mu times 46.98 newtons. And the force of friction? 10. 10 newtons. Okay, so mu is equal to 10 divided by 46.98 newtons. So the coefficient of friction is 0.21. Is that what I asked you for? Okay. So, what did you learn? Coefficient of friction is 0.21. That's true, but that's not, you should not have just learned that. You actually don't have to find the acceleration, right? If you get the force of friction and the force of friction actually just turns out like if they give you the force, then all you need to find is the normal force. You don't have to find the acceleration of the entire system. Now, it was really nice that we did, and I appreciate it because that gives us a little bit more information and it means that you can flex and know what you're talking about. But if it's asking you for the coefficient of friction, Keep in mind the formula. The force of friction is equal to mu sub n. I was just going to keep going down that route because y'all didn't stop me. I mean, like, if you're not going to stop me, I'm just going to keep going. I did that to you, and I don't feel bad either. In which one? You corrected me where? Okay, you're right. That's true. Yeah. I had to redesign my problem. That's true. So 18 had to become 10 in order to actually have this question work and not go crazy. Okay. Questions? Comments? Concerns? Donations? We have 10 minutes left. We can save the world in 10 minutes. What if it's not moving down the ramp? What if it's stuck? Oh, wait. Before kinetic friction or static friction? Mm, yeah. Sorry, I kind of got you mixed up on that one. I had to go back to this. In this case, this mu, this is a kinetic friction. So 0.21 is mu sub k. The static friction would be a greater value. Now, let's switch gears and let's go to a case where it's the same thing, but it's not moving. So the acceleration is non-existent. So I'm gonna make the same thing. Let's make an incline real quick. And you want to keep the same mass, same angle, same everything? Lazy people. Okay, yeah, that's fine. So 5 kilograms, 20 degrees, but it's not moving. Okay, so the acceleration moving down the ramp is 0 meters per second squared. It is still. It is static. It is not moving. The coefficient of friction is equal to what? Okay, no, I think. Hang on. I think you're just 5 steps ahead of me, is what you are. I don't think that it's crazy talk. I think you're just 5 steps ahead of me. So here's what I'm gonna do. What is the line of action? Okay, so I'm gonna make a dotted line that goes down like this. Okay, that means whenever I make my free body diagram, the up and the down are gonna be diagonal like this, and the left and the right are gonna be to the horizontal. Okay, it's like we're taking this and we're putting it upright. Okay, so if we do our free body diagram, here's the dot in the middle. We have some forces here. Okay, how many forces do I have acting on this object? Yeah. Okay, so you gave me one too many. Gravity, normal, frictional. The applied force is the applied force is The applied force is gravity. So there's only 3 forces acting on here. The applied force is gravity. So there's gravity going down. Okay. Whenever we drew it up here, let me go back up here just to make a point. Okay. Whenever we have it up here on the top one, it does look like we have 4 force arrows, right? But this 50 sine 20 and this 50 cosine of 20, those are both gravity. Okay. 50 sine 20 and 50 cosine 20 both come from the gravity force. Okay. That's why we have 4 forces up, like it's 2 components and 2 forces. Okay. For a total of 3. So we're going to do the same thing down here. Our gravity is going to get split apart. It's going to be broken into 2 components. So I'm going to make my little line of action to make sure that I'm not crazy. I'm going to go up, down, left, right. And what's going? I think which one y'all want to do first? Normal. Okay. Normal goes this way. Normal goes this way. Okay. This way to the right. 5 gravity, but it's not just gravity. I can't just do mg. This is going to be mg sine theta. Okay. Because if you, because gravity points straight down, so when you break that up into components, the up and down one's going to be mg cosine theta for the adjacent side, and the bottom side is going to be mg sine theta, the one that's just highlighted. Okay, that's the opposite side. The one going down is going to be mg cosine theta. The one going back is going to be your friction. Okay? Some people prefer, I like making the line of action, and I like making my force diagrams look nice and like straight up and down and left and right. Some people like to include the force of gravity and like break it up into its components so that they have like the force of friction going out this way. I don't like doing that. So I like to keep it like straight up and down and left and right like this. But it's kind of up to you. You can actually keep it the same way and whatever. It works out either way. So, um, is it moving? Okay. So is it accelerating? So no acceleration. No A. So what does that mean? The sum of the forces is equal to 0, which means that the forces are equal to each other. Yes. Okay. So I always write it like this. The sum of the forces equals 0. So that means that F and mg sine theta are the same thing. Okay. F and mg sine theta are the same thing. So that means that my force of friction is equal to mg, so that's 5 kilograms times 9.8 meters per second squared times a sine of 20 equals, well, that's just three things to multiply together. Because those are numbers. I can deal with numbers. 5 kilograms, 9.8 meters per second squared, sine of 20, we're good to go. 16.76? Okay. Did you use 10 last time? Oh, okay. Kind of thought they'd come out the same. What is it, 16.76? Okay, 16.76, we can round up, 16.76 newtons is equal to the force of friction. All right, so, but I also know that there's a formula for the force of friction. I know that friction is fun. Yeah, so the force of friction is equal to mu sub s times the normal force. Okay, all right, we have 16.76. We have the normal force, kind of. Is this thing Hulk smashing through the ramp? No, so that means your normal force is balancing out the quote unquote vertical component of gravity. Okay, so you're going to use mg cosine theta. So that's going to be mu times uh, 5 kilograms times 9.8 meters per second squared times the cosine of 20. We probably should have just used 50 like last time. What do we get? 46.04, so it's 16.76 newtons divided by 46.04 newtons. That gives you a mu sub s value of 0.36. And notice A, it's dimensionless, okay, because the newtons are going to end up canceling out. That is an important thing to add. And so it goes bye-bye, bye-bye. Everybody brought newtons to the party, so it goes away. 0.36 is a greater value than 0.24. That should be 0.36, I think. 16 divided by 46 should not be greater than 1, right? Okay. So yeah, we get 0.36. I think from there we're done. I think we've only got about 2 minutes left. So I'm going to call it there. Y'all make sure that y'all have homework 2.1 and 2.1 done this weekend so I can like give you points and we'll resume this on Monday.